Hi guys, this is video 4-11 to be watched Thursday, December 15th. We're on page 5 in the second packet of this current unit. There's no homework, and this should be much shorter than yesterday. So before we read this first example, I'd like you to write this down for yourself. And this is a graph matching tip. Okay, there's many ways to match graphs, because that's what we're about to do, like derivative graphs. Many ways to match them, but this is helpful. Look for zeros, extrema, and points of inflection, okay? Because if you have, just with this information here in our table, you could see that, okay, a sign change would occur at a 0. All right, so this point of inflection, if you've got a function and its first derivative and its second derivative, and you look down here at this last row, a point of inflection in the original graph, the x-coordinate of that point of inflection should be the same as should be the x-coordinate of an extrema in its first derivative, and the x-coordinate of a 0 in its second derivative. Okay, so if you can match a point of inflection with an extrema with a sign change, then you can kind of see the order that the functions should come in. Okay, so if you look here, so the graphs in this figure below are show as functions of time the position s, the velocity ds over dt, that's just Leibniz notation for s prime, and the acceleration a equals the second derivative of s with respect to time. That's just notation for s double prime. So it shows these three things of a body moving along a coordinate line. Okay, so just moving along some line. Which graph is which? Give reasons for your answers. Okay, so I'm going to look for zeros. And I see in graph A, I've got a 0 right there. Okay. I'm going to look for extrema. I see a local extrema. So I see this local extrema right there. Okay, that's all right. That tangent line is 0. And then I'm also going to look for points of inflection. I see a point of inflection right about there. And guys, you can see those are all lined up right there. So the question is, which one is the position function, which one is the velocity function, the first derivative, and which one is the acceleration function, the second derivative? Well, if you look at our graph, if you've got a point of inflection, an extrema, and a sign change all corresponding, you've got three different graphs and they're all lining up, then the point of inflection must have been on the original graph, in this case our position graph. The extrema would be on the first derivative graph, or with the velocity graph, and the sign change on the second derivative graph, or the acceleration graph. So I'll just say it like this. I said it, I'll say that s of t, okay, that's the position. I used s to be speed yesterday, but that's the graph C. V of t, which equals s prime of t, this is B. I found the inflection point on that one. I had the local extrema on that one. And then the acceleration graph, which is the same as V prime of t, which is the same as S double prime of t, is that one, okay? And then I'll say for my reasoning, because the POI on C corresponds to the extrema on B, which corresponds to the 0 on A. Okay. Now, here's another example. So long story short, when you're trying to match graphs, look for these three things, okay, because one will imply another. So particle motion, a particle moves, here's another example, along a line, so the position at any time t greater than or equals 0 is given by the function s of t equals that, where s is measured in meters and something is measured in seconds. I think it should have said in time, measured in seconds. So A, find the instantaneous velocity at time t. Guys, they didn't need to say instantaneous. If they just said velocity, you'd assume that it would be the instantaneous velocity or the instantaneous rate of change. They would say average if they meant average. Okay, so first, I just have to remind myself, and go ahead of me, guys, if you'd like, that the velocity is the first derivative of the position function, negative 3t squared plus 14t minus 14. Okay, once you've got the velocity function, guys, it will give you the velocity at any time t. So this is the velocity at any time t. B, find the acceleration of the particle at any time t. So the acceleration function is the derivative of the velocity function, or the second derivative of position, and it's negative 6t plus 14. This will give us, this function will give us the acceleration at any time t. Part C, when is the particle at rest? And if you go back to our very first day, a particle is at rest, and we need to know this by heart, when the velocity is 0. So I'm just going to take my velocity function, set it equal to 0, so I've got negative 6t plus 14 equals 0. Then t equals, okay, you have to use the crap, this is not velocity, that's acceleration. Negative 3t squared plus 14t minus 14 equals 0. This won't factor, so you have to use the quadratic formula. I already did, so I'll save us some time. So we get t 1.4514 and t equal to 3.2153 seconds. Okay. So for part D, describe the motion of the particle. At what values is the particle changing direction? So the best way to do particle motion, guys, like describing it, is to do it the same as you would the first derivative test. Because to know when the particle is moving right or left, or up or down, we just need to know when the velocity is positive or negative. So it's the same as the first derivative test, really. So I'm on part D. So this will be velocity. And I've got, okay, so like right here we've got 1.45. And then right here we've got 3.215. And I want to see where the velocity is positive or negative. I know it's 0 at these, so I got to see where it's positive or negative. If I plug in numbers to the left, I get negative. Between here, I'll get a positive, and over here, I'll get a negative. So what does this tell me? Well, we don't think of negative time, so I'm going to start my description like this. At t equals 0, the particle begins, I'll say begins moving left, because it's negative on that interval. Begins moving left. Okay, period. At t equals 1.4514 seconds, it changes direction and moves right. Okay, and then finally there's one more sign change. At t equals 3.2153 seconds, it changes direction again and moves left. It changes direction again and moves left. Okay, so that was for D. Oh, and I kind of answered that. I don't know. I answered this second part. I described the motion, and in describing the motion, I said at what values the particle changed direction. Okay, so finally, when is the particle speeding up? When is it slowing down? Explain. Let's cross out slowing down. That would be a good like opening quiz question for you. Not tomorrow, but like in the future. So make sure that you know how to do that. When is the particle speeding up? I have to know my facts. If you don't know your facts, it's just going to be so unenjoyable to do this. But if you know your facts, it can be very satisfying. So I have to know when it's speeding up. So I have to figure out where my velocity and acceleration have the same sign, either both positive or both negative. And if I can figure out those intervals, I'll know where it's speeding up. All right, I've already got a number line for my velocity graph. So I already know where velocity is negative or positive. Now I have to find out where acceleration is negative or positive and compare it with velocity. So I'll do part E up here. So I'll take my acceleration, set it equal to 0. Okay, and when I do that, I get t equals 2.3333 seconds. Okay, then I'm going to do this number line. Okay, so this will be my acceleration number line, and I've just got 2.33 right in the middle. I test points to the right and left back in the velocity function right up here, and I get positive, negative. Now, I think the best way to see this, guys, you're looking for a combination, an acceleration velocity combination. I'm going to take this number line and write it below here. All right, and just like line it up. So this is the velocity one. All right, so like over here I'll have 1.45, and then over here 3.215, and I'll put my signs on it. And I'm looking for where velocity and acceleration have the same sign. Well, this positive acceleration interval is overlapping with this positive velocity interval. And this negative acceleration interval overlaps with this negative acceleration interval. All right, so we don't have, all right, so if I go like, let me just go like that, maybe, if that helps at all. All right, so it's going to be, so here we've got this over, and I'll go like that. All right, so we're going to have this interval overlapping for both positive, and then that interval over, those intervals overlapping for both negative. So I'll say speeding up, and I'll just say the first interval, 1.4514, comma 2.3333, because a of t is greater than 0 and v of t is greater than 0. And then I'll say also, and I'm separating, I guess you could do a union of these two intervals, but I just thought, I don't know, I felt a little funny doing a union because it's speeding up on them both, but like for kind of different reasons. So, but I think a union would be fine, if you know what I'm talking about. So, and v of t is less than 0. Okay, guys, there's that. Tomorrow we will have our last video for this unit. And I will see you tomorrow. Bye-bye.